Thank you for having me at this event. It is really nice to be back here at Stony Brook. I grew up on Long Island, spent a lot of time on the North Shore, the South Shore, and since becoming an engineer, one of my real focus and areas and I'd say passions is finding innovative ways to treat contaminants in soil and in groundwater in the ground. So we're not removing them from the ground and we're treating them in place. Just really briefly, I'm going to go a little bit fast here. There's a few slides I'm probably going to skip over or really get. I can talk about PRBs for a much longer period of time. Chris has asked me to self-edit a little bit. Maybe we can trim a little time and get us closer to lunch. So ISOTEC, my company, we're a small business, and we are a in-situ remediation firm. We're implementing in the field a broad range of treatment technologies for treating chlorinated solvents, petroleum hydrocarbons, 1,4-dioxane, and we're starting to dabble in PFAS treatment as well, and heavy metals. We have technical experts on staff who've been designing and implementing and managing these projects for decades, as well as a really experienced field staff. Many of our field staff have been doing injections for 5 to 20 years. That's all we do. So we've heard a little bit about the science of denitrification, and so this presentation is going to focus on reactive barriers, primarily through injection, but I'll touch on some other aspects. So I want to just kind of set the ground for a denitrification PRB. As we've said, this is a process that's fairly well understood for wastewater. Bacteria are converting nitrate to nitrogen gas, and these are anaerobic bacteria in the absence of oxygen. And for an in-situ treatment or a reactive barrier, these bacteria, the denitrifying bacteria, are ubiquitous in soils. So they're already there. We just have to find a way to make them a little bit happier. And a permeable reactive barrier, or PRB is the acronym. I think Lee said we love our acronyms. There's 3 words there, and they're all very important to what we're designing. First is permeable. We're creating something that groundwater will flow through. It's a passive treatment, and we're not changing the groundwater flow paths. We're not making it less permeable. Reactive, in this case for denitrification, we want to create a zone where the denitrifying bacteria are active so that we can be promoting this biodegradation process. And a barrier such that the nitrate goes in, the nitrate does not come out. We're preventing further migration of this chemical in the groundwater. So why PRBs for nitrate? We're creating an interception zone or a barrier, and they can be focused on where the nitrogen flux or the concentration is the highest. We can treat point sources, non-point sources, nitrate that's been in the ground maybe for decades, that's on its way flowing to a coastal water body, and we can cut that off. And for watersheds where the total maximum daily load is the goal, we don't necessarily have to meet a target concentration. We're looking to remove as much mass as possible. And that is a contrast to a lot of the remediation that I do in situ, where we're trying to meet a certain concentration goal or a cleanup target for a site. And PRBs can be part of a nitrogen plan. So a lot of the work that I've done, I live in Massachusetts now. I've been working on numerous communities on Cape Cod, including in Steve's community. And so there's a Clean Water Act order from EPA to restore the coastal water quality. And these costs, I mean, and the previous speaker was talking about some of the cost of this. These costs are nearly 10 years old, but looking at sewering the entire Cape, $6 to $8 billion with a B. That's a lot of money, ultimately mostly taxpayer funded. If we kind of look at it, it's going to come from grants, federal, state, but where do those come from? Comes from all of us. So we're looking for ways, how can we do this more cost effectively, more innovatively? And there's a Cape Cod water quality plan that's looking at a combination of traditional wastewater with sewering and non-traditional treatments. Sewering high density areas, looking at PRBs in certain areas, innovative, the IA systems, shellfish aquaculture. Another component of and the ultimate goal is to minimize the area and the properties that need to be sewered. We talked about just that fraction of that breakdown, which also was a big dollar difference. One of the other aspects where PRBs are being looked at on Cape Cod is that for communities and neighborhoods that are looking to sewer, the cost to fund, design, and implement can be maybe over the next 20 to 40 years. And that's going to be a lot of wastewater that's getting into the ground before that. So can you design and implement a PRB rather quickly, get them in the ground, and even for a community or neighborhood that's going to be sewered, put a PRB in now and cut out their nitrogen transport towards your water body in the interim. I've got a little funny animation here. Okay, so carbon substrate donors. So what we're looking to do is we want to create anaerobic conditions that are favorable for the denaturifying bacteria in the subsurface. And what we'll do is apply a carbon substrate, and what you're doing is you're providing a food source for bacteria as well as a means so other aerobic bacteria are consuming the oxygen and then creating that anaerobic condition. And we have numerous options for carbon substrates. We have various liquid amendments. There's soluble or quick release amendments, methanol, high fructose corn syrup, molasses, as well as slow release amendments, including emulsified vegetable oil, which I'm going to talk about in more detail. And then there's, I'm going to go back, some of the solid products, which include mulch, which we've been seeing, some of the systems, compost, and even using soft shell crab shells has been used as in PRBs for remediation of groundwater. When we're looking to install our PRBs, my focus in my next little bit will be more on injection, and you'll hear a little bit more trenching and solid PRBs, the later speakers. But we also have options. For liquid amendments, we can inject through injection wells. These are typically PVC wells with a slotted pipe in the vertical interval of concern. Also with temporary injection points, advanced with a small geoprobe, probably not much bigger than this table. So small footprint, great access. And then for applying the carbon substrates, there's trenching, which can be put in with an excavator, or if you really need to get deep, a one-pass trencher. Or there's also PRBs looking at large diameter boreholes, anywhere from 10 inches and larger. And each of these installation methods has their benefits and their challenges. My focus is on injection. My company does 50 plus injections in any given year at sites all over the country for various contaminants. And so that's something that I do a lot of design implementation for. And injection wells, as I said, or injection points, you're installing them with a rig maybe smaller than this table. So it's flexible. You can get in, you can change points, you can move points, whether there's subsurface utilities, you have above ground, you've got trees, driveways, whatever the case is. As long as the drill can get to that depth, you can inject there. That's great. You have no depth restriction. And because you can create these radii and then larger with some migration of 15, 20 feet even, we get a very large residence time in our PRBs, which is great for groundwater flowing through. Longevity is a little bit of a question mark right now, and I'll talk about that on a few of the case studies. And there may be a need for a setback using through the UIC programs, the underground injection control programs. With solid amendments, one of the greatest benefits of that is longevity. The one case study that was talked about earlier, there was some PRB guidance documents in the remediation industry that are looking at mulch trenches and wood chip trenches that have been active for 15, 20 plus years for chlorinated solvents. And we can anticipate that for nitrate treatment as well. These can also be located very close to surface water because it's not liquid and your amendment is not going to be mobile. So that's great. With a trench, we are limited depth-wise. It's only as deep as you can get an excavator, typically 18 to 20 feet, and you also then need to bring in a large excavator into a neighborhood so that's disruptive. And then just like with the small borehole trenches, maybe even a 12-inch borehole, your residence time is limited because you're only going to have maybe 4 feet with a trench, maybe only 12 inches of thickness in the subsurface. So, but yeah, I think those are the biggest drawbacks of those. So I'm going to focus a little more on injections, as I said. And emulsified vegetable oil, it's food grade, it's soybean oil with an emulsifier just so it mixes and dilutes into the water so you can inject that. The emulsifier breaks down and those oil droplets settle in the pore grains. And this is widely used for biodegradation of chlorinated solvents in groundwater. This is just kind of an image on the right of a preceding, it's an image from a preceding paper I wrote more than 10 years ago for treating a 6-acre trichloroethylene plume in a forested wetland in Connecticut, just showing that we've been using EVO and PRBs for groundwater treatment for a long time, and it's really well accepted in the remediation industry. So it was that experience that got me involved in working with several communities on Cape Cod, very similar, sole source aquifers, sandy soils. 80% of the wastewater on Cape Cod is through septic, so very similar to Eastern Long Island. One of the first things we came through was just kind of working with the public. Prior to ISOTEC, I was with a consultant doing this and doing some design of this. I was going to public meetings in 2014, 2015, and they would look at me, "You're going to inject oil in the ground? That sounds terrible." And it's like, no, it's food grade, it's okay. And we do it all the time on hazardous waste sites. Wait, are we a hazardous waste site? Is the whole community a hazardous waste site? And I was like, no, nitrate's not a hazardous waste, you're okay. But then they were also like, well, it's oil, it's gonna get in the water, we're gonna have it Exxon Valdez, and so we were able to kind of reduce the concerns from the community and move forward. And then we said, well, okay, we've got the community on board, but there's a lot of implementation challenges. We're looking at treatment intervals and nitrate more than 70 feet below ground surface, not something you can get in with a trench very easily. Very fast groundwater, seepage velocities in excess of 100 feet per year. Looking at high fluxes of groundwater and nitrate, of oxygen and nitrate. And the oxygen fluxes are really important because these are anaerobic bacteria. So you need to remove the oxygen in your barrier before you're gonna have denitrification. Highly developed areas. There's some sites that have low pH. These are bacterial processes. Low pH can inhibit that. This community is looking at thousands of feet of PRB, thinking about where to put those. And the big question was, well, how long are these PRBs going to last if you're injecting them? And how often do we need to rejuvenate them? So what are the first things you do when you're kind of looking proof of concept? You go back to the laboratory. So a company that ISOTEC partners with is Terra Systems. They've been manufacturing bioremediation amendments for more than 30 years. They ran a series of column tests using groundwater and soil from sites on Cape Cod. And one of the things they found was that EVO in a column test is great for denitrification. Perfect, we kind of thought that would happen. However, their off-the-shelf emulsified vegetable oil started to see breakthrough in their column in about a year. That's not the news anybody wanted to hear, that we would not need to do these injections every year. They went back to the drawing board, they reformulated, they changed out their surfactant, they looked at what some of the other amendments in there, really looking for an amendment that's stickier to the soil, was gonna stick to the soil grains, particularly in high groundwater flow rate velocities, to extend the PRB duration. So that's this SRS-NR, which we'll see from some case studies. There's also some work that was done at Tufts University with a graduate student who I was co-advising, looking at denitrification kinetic rates and investigating the effect of pH on denitrification. There is actually a lower pH where denitrification stops. We found that. And now she's continuing her PhD, continuing to work denitrification issues. So to date, there's been 4 denitrification PRB demonstration tests on Cape Cod. They were injected somewhere between 2016 and 2020, all with emulsified vegetable oil. They were all 4 of them with the SRS-NR product, that reformulated product. And to date, we have 4 to more than 7 years of groundwater monitoring. The first was in the community of Orleans. And really the first objective of this was couldn't evaluate longevity. How long was this gonna last? The objective was, let's have a PRB that lasts more than 3 years. As I said, my previous job, I was with a consultant who was working with the town of Orleans, so I was the key designer on this, so I got to be the designer. And then somewhere between design and the implementation, I switched over to ISOTEC, so I've been able to kind of see both sides of that. And this was installed with temporary injection points. So there's one of these direct push rigs. We can see just the temporary injection points along that line. And that white line I added, but that was the PRB line. It was done in a middle school parking lot while school was in session. So pretty low impact. So how did it work? One of the first things that I was curious about is, how was this stickier and EVO gonna work? And the first thing that we saw during the injection was the monitoring wells that were 6 to 10 feet down gradient of the PRB. We did not see breakout during the injection. It has a white color. We see that. I've been involved in dozens of EVO injections, and it's not uncommon to see your EVO during the injection event show up in a monitoring well 5 to 10 feet away. So I actually saw that as a good sign in that stickier EVO was probably getting stuck to the sand grains and not migrating as it was being pushed out. Since then, since 2016, we've got more than 7 years of data, and kind of as expected, if this is going to work, yeah. So initially, we saw that our oxidation reduction potential decrease. We saw our total organic carbon concentration increase, which is the food, which is the EVO that we injected. And then we've seen our EVO, our nitrate concentrations remain low 7 years later. Another way to look at this, and I think this is a great visual for the effect of a PRB. So on the left side, we have pre-injection concentrations in the fall of 2016, and nitrate concentrations in the wells range from anywhere from 3 to greater than 20 milligrams per liter. Post-injection, so this is 3 years post-injection, we can kind of see down gradient, if I'm getting that right. Most of the monitoring wells immediately downgraded in the PRB are below detection limits. So that we drew a line. That is that barrier. We were able to create conditions favorable for anaerobic denitrification in the subsurface, and we're cutting off the nitrate from flowing beyond this demonstration test. Another one, just in Stevens community in Falmouth. This was funded through an EPA Southern New England program grant, and this site was chosen because it was town-owned, and there was some previous investigation on this site and nearby. So we already had some data as baseline. One of the things we were looking at this site, which we thought was very interesting, is it was reported that the groundwater flow rate was much faster than it was at the Orleans site. So let's try a PRB at a fast groundwater flow rate. The team that I was on with ISOTEC, Woods Hole Oceanographic, we ended up looking at did more of a hydrogeologic assessment, and groundwater flow the seepage velocity is almost an order of magnitude slower, which in some ways is good because you get longer residence time, but your flux of nitrate is lower, so you may be removing less pounds of nitrogen per time. But it just shows the importance of really identifying your hydrogeologic conditions. And we applied 2 dosages. The concentration to the dosage of the EVO is a really important cost factor. So we actually were trying to see failure in the 2-year grant monitoring period. We just got data about last month, and 46 months later, it's still working and working really well. So that gives us a good sense that these EVO PRBs are going to give us long longevity. So just a few other observations from all of the Cape Cod. Wide range of nitrate concentrations. One of them had nitrate at 1 milligram per liter. One of them had 40 milligrams per liter. And we're seeing effective denitrification across all of that. One of the Martha's Vineyard tests looked at measurements of nitrogen gas, showing that we're seeing full denitrification. And the Falmouth study I didn't mention also did an analysis for nitrous oxide gases, which are also a greenhouse gas. We don't want to be putting these PRBs in and increasing the greenhouse gases out of our PRBs. And these 2 studies show that that's not the case. Summarizing all of these 4 studies, as well as ISOTEC's experience, TerraSystems' experience over decades of doing injections and other PRBs, there's an engineering design manual that was prepared through that SNEP grant. That's available for download. If anybody wants to download that, please see me afterwards. I can send you the link, or I'll email it to you. I'm going to skip over these few slides. They're more about design. There's some more details on that. I could talk about design of PRBs on and on and on, so if anybody wants to talk about that. But I do want to take the time and get to some of the dollars of this. This is a question that we get a lot, and I'll touch on a few of those design parameters in there as well. So as for cost metrics, the 2 that I get asked about the most are dollar per pound of nitrogen removed, as well as dollar per linear foot of PRB. So let's kind of break those down a little bit. Acknowledging that there's a lot of sensitivity in both of those metrics. So it's not quite you build a wastewater treatment plant, here's your flow in, here's your flow out, here's how many $1 million it costs to build it. For any given PRB, it was mentioned earlier, a lot of these remedies have to be site-specific. So when you think about what is the nitrate concentration, what's your soil permeability, your groundwater velocity, those all add up to groundwater and nitrogen flux. What's your vertical impacted zone? Do you have an 8-foot zone where you have a really large nitrate plume? This is on the bottom right here is one of the PRB sites that had a vertical monitoring every 4 feet. So we can really see that you can, in the shallower groundwater, there was a significantly higher nitrate concentration. That was a great vertical area to put a PRB. What depths what are your other electron acceptors, oxygen, sulfate, for example, and what is your length of your barrier as well? So if we look at dollar per pound of nitrogen removed, for the cost, it's generally time and materials. It's how long is the injection team in the field, what equipment do they need, and their materials, which is primarily the reagents, the EVO, but maybe some pH buffer, maybe if you need a water permit, things like that. And then your pound nitrogen removed is your nitrate concentration, your groundwater velocity, your vertical interval, all things that get into that pounds of nitrogen. And just some of the ranges of some of the sites on Cape Cod where we've done PRBs, we think about 4 to 20 milligrams per liter, the vertical interval, the groundwater velocity. This can vary pretty much. So a community asked me recently for a rough cost for an 1,100-foot linear PRB. They didn't have all the investigation yet, so we looked at scenarios for a 16-foot vertical interval as well as a 28 vertical interval, just kind of for planning purposes. Assuming 8 to 10,000 gallons a day of injection, those two scenarios came up with anywhere between 9 and 20 injection days. And then if we look at pounds of nitrogen removal, it really is flux times how many years is your PRB going to be in place. So for that dollars, time, materials, somewhere between $600,000 and $1.2 million for this PRB. And that was two rows of points as well. Pounds of nitrogen removal along those sensitivities of concentration, flow rate, vertical interval, length, range anywhere from 50 to almost 2,000 pounds per year, so wider range. Using the Orleans PRB, the first one that I showed, came up to about 150 pounds per year, using their loading. Assuming a 7-year lifetime, but we also acknowledge that our first PRB has been in the ground for more than 7 years and it's still going, so it's probably longer than that. Seeing somewhere between about 300 and 13,000 pounds of nitrogen, so we're ranging by a factor of 40. The longer these PRBs run, the lower that cost goes for pound of nitrogen removal, but it was somewhere between 50, which is really inexpensive for removing a pound of nitrogen, to more than $3,000. It's really importance of that site-specific characterization, really locking this in, understanding your fluxes at your locations. Just one other item I'll throw in for PRBs. I'm also starting to get some questions about, well, maybe not doing a 1,000-foot PRB, but what if we did them at a small scale? What could this also be an alternative to a new septic system, an IA system? There's a lot of residents who don't want to have their entire lawn dug up to put a new system in. If we can come in with a small rig size of this table, the injection rods we install are 1.5 inches in diameter, so we're basically advancing a small number of 1.5 inch rods. Maybe we rip up the grass a little bit, we put a little bit of new grass seed down, we do this in March, and by July their grass looks good as new. So that is also another alternative that's being investigated in some of these communities. I looked at a scenario for a 50-foot long PRB, 8 feet thick, just at the water table. Came up with plus or minus $30,000. That's plus or probably 20% costs. And really costs for IA systems can range anywhere from $15,000 to $70,000, depending on the size of the system and the like. So it's right in that line, depending on access, limitations, cost, and the like. So just kind of conclusions, a few next steps. We're seeing that the costs can potentially be, if you have a high flux zone, smaller capital costs than sewer and wastewater treatment. So it can be part of that overall plan. It can address point sources and non-point sources. Very small footprint, limited disturbance, which is a real benefit. And they can be used in combination with sewering over time, using with IA systems and the like. And now on Cape Cod, there's communities that are looking at 500-foot PRBs to more than 2,000-foot PRBs, and there's one community that potentially, if you look at community-wide over the next 10 to 20 years, they may want to have upwards of 30,000 linear feet or PRBs in combination with sewering, in combination with aquaculture, and just how are they going to meet their TMDL goals? So with that, I thank you. And I also have a poster outside, or feel free to email me or call me anytime. Pretty passionate about this stuff. So thank you.